Okay, so there's relatively little for us to fill in terms of notes for this lesson, but I do want to say something kind of before we start. If we look at this lesson and you look at the steps that we're going to go through, and then you go back to Unit B and you look at Lesson 4 where I told you how to predict redox reactions, these are basically the same steps. I've just replaced oxidizing agent with acid and reducing agent with base, but it's the same general principle. The table that we'll use in your data booklet is different. Of course, we're going to use the acid and base table. But the setup is the same. Highest on the left, lowest on the right are the strongest, just like they were for oxidizing and reducing agents. So when we're talking about predicting acid and base reactions, we have to consider that there's a proton that's being transferred. In redox reactions, it was an electron that was being transferred, but this time it's a proton that's being transferred. So what is going to happen? Well, whatever the strongest acid there is in the system, that's the thing that's most likely to donate a hydrogen ion, so a proton, to the strongest base. And it's the thing that's most likely to accept it. So in Lesson 9, we said an acid is a proton donor, a base is a proton acceptor, and so that's what we're going to base this on. One thing that's important is that we're going to assume that only one hydrogen is transferred in each reaction. If an acid, let's say, had more than one hydrogen that it could donate, we would write 2 separate reactions or 3 separate reactions. So for each individual reaction, we're only going to transfer 1 proton at a time. Now the steps that you have to follow are listed here. First, you list everything that's there. Whatever ions or atoms or molecules you have. That's the same thing we did for redox reactions. List everything that's there. Then we identify the strongest acid and the strongest base. Just like in redox, we identify the strongest oxidizing agent and the strongest reducing agent. Then we transfer 1 proton from the strongest acid to the strongest base. And when we do that, the products will be the conjugate acid and base. So if you remember what a conjugate pair is, it's 2 substances or 2 molecules that are different by just 1 proton, just 1 hydrogen ion. So that's how we'll determine what our products are. The last thing that we need to do is predict the equilibrium position, if there is one. So we're really saying which side is favored. The products will be favored. So the percent reaction would be greater than 50%. You probably wouldn't have to calculate that, but we could give you that number, greater than 50%. If the strongest acid is higher than the strongest base in the table. That was the same sort of principle as we used for redox. If the oxidizing agent was higher than the reducing agent, it was spontaneous. Here, we're going to say the products are favored if the acid is higher than the base. The reactants are favored, so less than 50% of them will react if the strongest acid is lower than the strongest base in the table. Now those are our instructions. Does anyone have any questions about them? Okay. Now it's possible that there isn't an equilibrium because sometimes reactions can be quantitative. A quantitative reaction means 100%. All of the reactants become products. And if that was the case, we wouldn't ask you which side is favored because there's no equilibrium. All of the reactants turn 100% into products. Now I have 3 examples here that we'll go through just to help you practice doing this same sort of setup of steps, but for acids and bases. The first step tells you to list everything that's present. So I'm going to start by saying, well, I have a solution, so there's water. My solution is magnesium hydroxide, so I'm going to write out those 2 ions separately because it said it was a solution and ions dissociate in solution. It also says I have benzoic acid. You might not remember what the formula for benzoic acid is, but you could look it up. Benzoic acid is C6H5COOH. Now that we've listed everything, we have to figure out what's the strongest acid and what's the strongest base. So that's where you use the table that's in your data booklet. Now, much like with redox reactions, water is on this table, but it's not particularly strong. If you locate water, it's the lowest thing on the left. That means of all the potential acids listed here, it's the worst one. It is the least strong. It's also on the side of the bases. Remember, bases are stronger at the bottom and get weaker as we go up, and water is close to the top. So water is a pretty weak acid and a pretty weak base. It is very unlikely that it will act as the acid or the base unless there's nothing else present, unless there's no other choice. So water could be an acid or a base, maybe. When something can be an acid or a base, does anyone remember what it's called, what the term is for that? It's a vocab word. It will certainly be the top. It does start with an A. Yep. Amphiprotic, that's the word. Yeah, you were pretty close. You knew the first letter. And you know what? If it had been a multiple choice question, that might have been enough, knowing the first letter. So substances that could be an acid or could be a base, amphiprotic. Now the next substance, Mg2+, do you see it anywhere on this table? You will not. This is just a spectator. It's not doing anything. It's not going to act as an acid or a base, so it's not going to be part of the reaction. Hydroxide, hopefully you remember, that is what strong bases have. Hydroxide is the strongest base that's on the table. So I'm going to decide right away that hydroxide is going to be the base because there's nothing else that's stronger than it. So I just need to decide which thing is going to act as an acid. Frequently, because acids have the word acid in their name, it kind of gives it away. But I would still check just to make sure. Benzoic acid is right underneath the fold in your data booklet, so it's the first one on the second page. It is certainly a stronger acid than water. So those are my two choices. I'm going to pick benzoic acid as my acid and hydroxide ions as my base. So when I write out my reaction, it doesn't matter that I wrote the acid first and the base second. So you could inverse those. What is important is that I recognize what's going to happen. My acid is going to donate a proton to my base. Now there were lots of hydrogens in benzoic acid, but I picked the one at the end on purpose because it's part of the carboxyl group. That's the part that makes it an acid. The hydrogens that are attached to carbon at the beginning of the molecule, they're not going to react in an acidic type of way. Only that one that's part of the carboxylic acid group. So what do I have as my products? Well, I have this. Now, how did I know that? Well, I took off the hydrogen. If I was unsure what the product should be, I could also use my data booklet and see that the conjugate base of benzoic acid is C6H5COO negative. My other product will be this hydroxide plus the hydrogen ion, the proton that I donated. So H2O will be my other product. If I wasn't sure, I would look at my table and say, the conjugate acid of hydroxide ions is H2O. Now the last thing we have to say is which side of this reaction is favored. So the rule is if the acid is higher than the base, products are favored. If the base is higher than the acid, reactants are favored. If you look in your data booklet, I'm going to say that the products are favored, and that's because benzoic acid is up here and hydroxide is way down there. Okay, now in the next one, I have ammonia, which is NH3, and sulfuric acid, which is H2SO4. Now, if you look on your table, you'll locate ammonia and you'll see, oh, it's on the base side of things. So down here in my table, it's in the conjugate base column. That's where I'm looking. And it's close to the bottom. It's not as far down as the hydroxide is, but it's close. So it's a few up from there. H2SO4, sulfuric acid, is going to be my acid. It's quite high. It's above the gray line, which means it's a strong acid. Strong acids ionize 100%. That was our description of a strong acid back in lesson 7. So if you have a strong acid and you place it in water, are you actually going to have any H2SO4 left? You won't. What you'll really have is hydronium. So if you have a strong acid, rather than writing the formula for the acid, you can directly write hydronium because that's honestly what you're going to have. So if we were to write this reaction, we would write H3O plus NH3 . Now I still have an equilibrium here. Even though my acid is strong, my base isn't. The only time we wouldn't write an equilibrium is if both of them were strong. Same thing will happen as before. I'm going to take a proton from the acid and donate it to the base. And if I wasn't sure what the products were, I would look at my data booklet and look in the opposite column. The conjugate base of H3O is H2O. And the conjugate acid of NH3 is NH4+. Now the last step is to predict the position of the equilibrium, which side is favored. Since my acid was a strong one, it's higher than my base. And so I would again say that the products are favored. Now the last example is one where we have a strong acid and a strong base, just so you can see how it would look. I have a solution, so I have water. I have lithium hydroxide. Because they were in solution, it means I have those ions. And then I have perchloric acid. Since perchloric acid is the strongest acid up here, it'll follow the same pattern as sulfuric acid. And we'll say that all of it is going to ionize, and so I will essentially have hydronium. Now here's why it would look different when I have a strong acid and strong base. Hydronium will be my acid. It's the strongest thing that could be an acid. Hydroxide will be my base. And I'm not going to draw an equilibrium arrow. I'm going to draw a quantitative arrow because when a strong acid reacts with a strong base, there's no equilibrium. The reaction is quantitative. 100% of the reactants should react and form products. Now, can somebody tell me what my products are going to be here? I'm going to transfer a proton from my acid to my base. Water and water. So when I transfer that proton, I'm going to have H2O and H2O. Now you could simply write 2H2O and not write the second one there. But when you have a strong acid reacting with a strong base, water should be your product. That's what should happen.